Afternoon. I'm spot on weather meteorologist Matthew Euler. Welcome to my latest training. This training video, we are going to cover the topic of pressure system intensity changes. For today's overview, we're going to look at four main processes involved in mid-latitude cyclones as well as mid-latitude anticyclones. These terms are called cyclogenesis, cyclolysis, anticyclogenesis, and anticyclolysis. All right, so there's four main processes that are affecting surface pressure systems. Let's get into the definitions of the four terms from the previous slide. When we talk about intensity changes of pressure systems, both low and high pressure systems across the mid-latitudes. Cyclogenesis is the formation of a new low pressure, or it can be the intensification of an existing area of low pressure. Then you have cyclolysis. It's the filling and dissipation of a low pressure. The anticyclogenesis is the formation of a new high pressure system, or it can be the intensification of an existing high pressure. And then we have anticyclolysis, which is the weakening and dissipation of a high pressure. I always thought the cyclolysis, that term right there kind of makes me think of maybe some kind of villain or something in any kind of the Marvel movies or something, just kind of a little side joke there. But these are the four main processes affecting surface pressure systems. All right, so let's examine what causes the cyclogenesis to occur. Cyclogenesis being the development of a new low pressure system or the intensification or deepening of an existing cyclone across the mid-latitudes. It's primarily caused by divergence aloft in those upper levels. We've hit that pretty hard the last few training videos I put out. So please go back and take a look at I'd say the last four videos. We talk about vorticity, we talk about the different types of atmospheric waves, and we talked a lot about divergence aloft and how that removes mass from the air column in the vertical. Divergence aloft, there it is, removes the mass from the air column, and when that happens, we get upward vertical rising air motion and decreasing or falling surface pressure. That is going to help in the process of cyclogenesis, right? This decreasing surface pressure causes an increase in the surface pressure gradient with stronger winds and increased cyclonic curvature. When we talk about cyclogenesis, we must talk about one specific rule that's very, very important in meteorology, and this was developed by Sverre Pedersen, and it's called Pedersen's rule. I remember when I went through meteorology school how I had to always remember this one. Basically, I had to memorize it because it was such a key concept of cyclogenesis. So what did Sverre Pedersen say per his rule? He said that cyclogenesis will occur when and where an area of upper level divergence indicated by PVA, the positive vorticity advection, becomes superimposed over a low level frontal zone across which thermal advection is weak. Okay, so let's examine this diagram here on the right hand side. Let's examine this. We have this black L, which represents an area of surface low pressure. We have a warm front extending outward to the east from this low pressure center. And then we have a cold front extending south and southwest of the low pressure center. All right, so for Pedersen's rule, what we have going on in the upper levels of the atmosphere, let's go ahead and just draw a 500 millibar. Let's call this a 500 millibar shortwave trough. And remember, the lowest heights is going to be the area where the greatest cyclonic turning is literally called this trough axis, denoted by this solid red line right down the center of the trough. All right. Now, out ahead of shortwave troughs, now let's say this is at 500 millibars, the shortwave trough, right? This is 500, and we'll abbreviate millibars with the letters MB. So we have a 500 millibar shortwave trough. It's moving west to east in the mid-latitude westerly wind belt. And out ahead of this shortwave trough axis, right here where my circle is, this is going to be an area of PVA, positive vorticity advection. Go back to my vorticity videos. There's two parts, vorticity part 1 and vorticity part 2. But specifically vorticity part 2 training video, I go into PVA and kind of like what it is and how it's represented on that 500 millibar vorticity chart. But anyway, we got this PVA out ahead of the shortwave trough axis. PVA, positive vorticity advection, is an indicator of upward vertical motion in the atmosphere. So the air is going to rise through a vertical column beneath this area of PVA. I'll just draw an up arrow like this. That indicates rising air from the ground up into the upper portions of the atmosphere in association with the PVA out ahead of this shortwave trough axis. Now let me draw a dashed line. Okay, this dashed line is my connection from my shortwave trough at 500 millibars down to my surface low pressure system here. So this area PVA is basically becoming superimposed over this frontal boundary. That's what we're saying over here with Pedersen's rule on the left. Cyclogenesis will occur when and where an area of upper level divergence, which is associated with this shortwave trough, becomes superimposed over this low level frontal zone across which thermal advection is weak. Now, how do we determine when we have weak thermal advection by strong thermal advection? We would look at the packing of these isotherms, lines of equal temperature. Let me draw out what a weak thermal gradient would look like. Thermal advection is going to be weak in this situation, okay? So this dashed line, let's just say this dashed line represents a certain value in degrees Celsius. I don't know, let's just say it's 15 degrees Celsius, let's say, and then we have another line north of that, okay? Let's say that's 10 degrees Celsius. Then we have another line way down here to the south, beneath or to below the other two dashed red lines, isotherms, and let's say this is 20 degrees Celsius. All right. So when we talk about weak thermal advection, we're looking at the spacing of these lines here, these isotherms. When they're farther apart, that's weak thermal advection. When they're more tightly packed, here, let me do this here. Okay, so let's just call this 25 degrees Celsius. That's 25 degrees Celsius. Okay, so when you have very tight packing of these isotherms, let's say we got lines like this. Okay, let's say we have lines like this. Now I want to compare here spacing. So this is an example of a strong thermal gradient. So that's an S for strong. See how close these lines are to each other? That indicates we have a sharp air mass change occurring. Potential thermal advection is stronger in this case, especially if you get a lot of wind. Okay, that's going to bring in these isotherms or this temperature change into your area. The further apart, now let's just look at the isotherms here, 15 and 20 degrees Celsius. See how much further apart these two isotherms are to each other? That is indicative of a weak, I'll put a W here. That's a weak thermal gradient based on the spacing or the packing. How far apart these two dashed lines are, these isotherms, lines of equal temperature. That's a weak thermal gradient. This over here on the right, bottom right that I just drew, I packed in a bunch of isotherms, these dashed lines. This would be an example of a strong thermal gradient, okay? We usually get strong thermal gradients during the fall and the winter time. And we usually get weaker thermal gradients or further apart spacing of isotherms during the summertime. All right, so we kind of describe everything here in Pedersen's rule, the definition. Cyclogenesis will occur when and where you get this area of upper level divergence, the top right portion of the diagram I drew here with this 500 millibar shortwave. That is got PVA superimposed over a low level frontal zone. Now this is my frontal zone, which has thermal advection is weak, right? So this is where you're going to get this connection between 500 millibar shortwave trough and PVA out ahead of it and your surface low pressure system leading to cyclogenesis. Now with cyclogenesis, a baroclinic low is going to require some sort of stationary front and a tight thermal gradient to form along it. Stationary fronts are usually associated with weak temperature advection. where weak pressure gradients exist with little thermal advection but a tight thermal gradient. And as a major shortwave trough approaches the thermal gradient, pressure begins to fall throughout the area. Temperature advection begins as the cold air moves south and the warm air moves north. This is getting along the line. So let's say up here in the upper right, just this upper right hand section here, let me just draw out an example of what a stationary front would look like. This red line. Now believe me, this isn't the right colors for it. Just bear with me here. Normally you'd have alternating red and blue on this line, and these little half semicircles would be shaded in red, and then these down here would be shaded in blue. I don't believe I have the capability, or maybe I do. Let's see, hang on here. Okay, hang on. I do have the capability. Okay, awesome. Okay, so let me redraw this now for you, and we'll make sense of this. Let me go ahead and erase all ink on slide, boom. And then we're going to go, and I'm going to draw this out for you. Okay, we'll start with red. Okay. Now you're going to have, for a stationary front, you're going to have semicircles. These normally are going to be filled in with color. They're going to be shaded in red, these semicircles, okay, on the line. And then you're going to have, let me go to blue now, my blue. You're also going to have, here we go, okay. This is what a stationary front's going to look like on a surface weather chart. It's going to have alternating, this is a triangle, but this is a stationary front, okay? And what you have going on is you have a tight thermal gradient, so let me draw that out for you, which means what? A tight thermal gradient means these lines, these dashed black lines in this case, are tightly packed. See how close they are to each other? That means I have a tight thermal gradient. I have a bigger temperature change over a shorter horizontal distance when I have a tight thermal gradient. Now what happens over time is we get an area of low pressure. Now let me go do this here. Go back to red here. What happens over time is you get one of these situations to occur. So there goes your warm front. Okay, here's your half semicircle. You get an area of low pressure here. All right. Then you get a cold front coming down out of it. Let me draw that out for you. So a cold front comes out of the low like this. Of course, these triangles are going to also be colored in blue. All right. These are triangles. All right. So you get a wave of low pressure to develop along this stationary frontal boundary. We have a tight thermal gradient over here on this side of the front, north of the front, the poleward side of the front, very tight thermal packing. Get an area of low pressure to develop, and then what happens over time, let me get my black ink back out, you're going to have a situation where these thermal lines are wrapping around this low like this. These isotherms, they're going to remain very tightly packed, close to each other. But what happens is you're getting a sharp gradient here with these thermal packing lines. And what you get going on, what happens when you get that low pressure developed along the front is you get the winds starting to turn cyclonically like this. All right. And it's starting to cause the warm air. We'll just label warm air with a W. And we'll label cold air with a C. Cold air is starting to move southeastward. Warm air is starting to move northeastward. Okay? And that's what happens. You get the upper level shortwave trough, PVA. You get a wave of low pressure to develop along a stationary boundary. This is going to be S for stationary over here. And then it becomes what you see in the upper right hand corner where you're getting, you got really tight thermal packing like this across these frontal systems, and as the air masses begin to move towards each other. This advection, by the way, deepens the upper level trough aloft, further increasing upper level divergence ahead of the trough, that shortwave trough, which deepens the surface low. So it's all connected. Thermal advection, get a wave of low pressure to form along the stationary front. You start getting thermal advection to develop, where cold air is moving towards warm air is moving toward cold air, and then aloft with this 500 millibar shortwave trough, you're getting, as this advection deepens the upper level trough, you're getting further increasing upper level divergence. So you're removing air much faster aloft at the top of the air column ahead of the shortwave trough, which is going to accelerate your low level convergence and accelerate your upward vertical motion as a result. All right, so in the upper air, an area of divergence is required for cyclogenesis. That's why we pay so much close attention to these shortwave troughs. The main areas where cyclogenesis occurs is going to be ahead of that shortwave trough because you have that positive vorticity advection, the PVA above that low, at and just downstream of the long wave trough axis, and where there is generally going to be diffluent flow aloft, height contours spreading further apart, and also ahead of an approaching jet maximum, that left front quadrant. So this right here, these are the areas. Let me draw this out for you now. So we want to say cyclogenesis, development of a surface low pressure system or intensification of it, ahead of the shortwave trough. So here's your shortwave trough again, here's your shortwave trough axis, here's your area of PVA out here. Okay, I'll just label with a P. All right, and let's say this is your surface low here. Again, that PVA up here, PVA, the upper level divergence, is helping to deepen the surface low pressure system. So let's say this is the surface, and this is 500 millibars. All right, additionally, we talked about this during atmospheric waves, part 1. We talked about long waves and where we generally see the favorable area for low pressure to develop or intensify. If this is my long wave trough, low pressure at the surface is most favored to undergo cyclogenesis, generally at and just downstream of the long wave trough axis. So generally in this area right here. And where there's diffluent flow aloft, because with diffluent flow aloft, I'm going to show you an example of diffluent flow aloft here. See how these lines spread further apart here over time? This is an example of diffluence. And what you're doing with diffluence is you're removing mass aloft much quicker than what's coming in at the surface. And again, if we use the length of the arrow as an example of strength, you can see that my arrows here in the upper portion of the air column are longer, which means they have greater magnitude. I'm removing mass quicker at the top of the column here than I am with low level converging at the surface. My low level convergence is weaker than what's being removed aloft. I have stronger upper level divergence aloft, okay? That's that chimney effect again, which we've really covered extensively. Ahead of an approaching jet maximum, if I were to show you a jet maximum here, it looks like a football actually, it's like an oval football shape, divided up into those 4 quadrants. If I'm in that left front quadrant over here, or if I'm in the right rear quadrant over here, those are my 2 favorable areas for cyclogenesis to occur. All right? So really, these are your 4 areas where cyclogenesis occurs. Keep in mind that this image in the upper right, that's your long wave trough axis, or LWT, long wave trough. And then just at and downstream of the long wave trough axis, which is this black solid line, there's your diffluent flow as your height contours spread further apart. When you have the upper level mass being removed quicker than what's being brought in at the low levels of the air column, that indicates falling surface pressures and low pressure here at the surface. Okay. And then this connection again with the upper level shortwave trough at 500 millibars and that PVA out ahead of it. And there it is. So cyclogenesis occurs ahead of a shortwave trough where there's significant upper level divergence. The surface low is situated directly below the area maximum divergence, so that it is not directly beneath the upper level trough. The upper trough is going to stack back into the colder air aloft. This is an excellent example. So let's just look. This surface low here on the right is represented by the letter L. That's your surface low pressure. Again, I'll mark the front W for warm front. That's this piece extending eastward. And then I'll mark this cold front. You see the blue triangles. This is C, cold front. Okay, you got your surface low. But look what's helping develop the surface low. What's deepening or intensifying the surface low? Let's see. We have upper level divergence here out ahead of the 850 millibar shortwave trough. We've got positive vorticity advection out ahead of the 700 millibar shortwave trough. And then we've got PVA out ahead of the 500 millibar shortwave trough. Let me draw a line. I'm going to draw it in a different color so you can really make it out. Let's do green. See how it's stacking back? Look at this. Look at that. This is your surface low at the surface. Look how it's stacking back with height. I mean, this is just ideal. And anywhere where you see this P, that's the area PVA out ahead of these trough axes on each level. This is an example of a major shortwave trough. It's showing up at more than one level. Okay, but all the PVA is basically being superimposed over this low pressure at the surface. I have a tighter thermal gradient, and I've got just great support for this low pressure system to strengthen. If it's not already developed along the stationary front, to develop, get a wave to develop along the front. So once the low has started to form, it requires certain conditions to continue deepening. The low must still have that upper level divergence aloft associated with the shortwave trough, and that shortwave trough needs to remain back in the cold air so that divergence aloft will remain strong. Now there's going to be a case, and I talked about this on my last video with barotropic systems. Let me see if I can draw it out for you here. I'm going to change the color back to black. I want to really hit this hard here. Okay, so cyclogenesis is favored under these conditions, right? But eventually what happens is your shortwave trough here at 500 millibars, okay? Your shortwave trough, let me draw it out completely here. Eventually it becomes vertically stacked above your surface low. Let's go down here now, whoops. So let's say this is your surface low. So this is the surface here. Eventually what happens is the 500 millibar trough, it's going to move west to east. It's going to move quicker than the surface low is going to move to the east. Okay? So what's going to happen over time is this area of PVA out ahead of the shortwave trough axis is going to outrun the surface low. And once this trough axis passes the surface low, you're going to have sinking air motion, which is going to fill the air column. Okay? So you have to watch the position and how these troughs are in relation or orientation to your surface low to determine if you're still favorable for cyclogenesis or whether you're going to enter a weakening low pressure system at the surface. On the surface, warm air and heating will assist in the deepening of the surface low. Why warm air? Why heating? Because warm air likes to rise. Warm air is going to rise, create that upward vertical motion that we need for cyclogenesis. And the warmer the surface the low is over, the more intense the rising air motion in the vertical. This is known as a diabatic warming effect. I'm sorry, I just crossed it out. Diabatic warming effect. Okay? So, low pressure systems usually try to seek out warmer surfaces because these warmer surfaces are going to promote more rising air motion. And whenever you go over a warmer surface, that's known as diabatics. Now, cyclolysis, on the other hand, is the filling and dissipation of a low pressure system. Cyclonic circulation is going to weaken, central pressure is going to rise, the air column, that pressure is going to fill. Most effective way for this to occur is losing the support of the upper level shortwave trough. That's what I mentioned right here in my drawing on this slide where this X is. That's what I'm talking about here. This PVA is outrunning the upper level shortwave trough. There's no friction, so it's moving quicker, eventually overtaking your surface low. And then once that shortwave trough passes, you have sinking air motion at NVA. That's going to result in sinking air and filling of the air column. That's what we're getting at right at this point, right here with this point, this bullet. The major shortwave trough that is supporting the low weakens, speeds up, eventually overtakes the low, and as that shortwave moves past the surface low, it brings an area of upper level convergence over the low, filling the surface low. That's the one thing I forgot to mention over here on this side, right? Here, let me do it a different color. I'll do it in blue. All right, so the backside of the shortwave trough, guess what we got? We got NVA, all right, negative vorticity advection, and we also have downward vertical motion here. Low pressure at the surface does not like this. Low pressure at the surface wants upward vertical motion, UVM, not downward. Additionally, we have ULC, upper level convergence back here, past to the west of that shortwave trough axis. All right, and that's what's going to result in filling the air column. Cyclolysis, here we go. A low will also fill through diabatic cooling. So if we have a low pressure that's moving over a cooler surface, it's going to promote more dense air and sinking air motion, not rising air motion, and that's going to kill that low pressure system basically. Cold air tends to sink, counteracts the upper level divergence aloft, and without upward vertical motion from divergence aloft, this will eventually fill the surface low and cause it to dissipate. All right, so let's take a look at this. All right, these two examples over here on the right-hand side, right? So we have our shortwave trough moving west to east here at 500 millibars. So this is at 500 millibars, let's say. I'll just draw 500 out. This is your surface low down here, okay? This isn't a favorable, this right here is a favorable position if I drew a dashed line back from the surface low to this 500 millibar shortwave. This is an excellent position for this low to continue undergoing cyclogenesis because our area PVA and upper level divergence is out ahead of this shortwave trough, and it's helping to result in greater rising air motion here for the low. So this is favorable. This where I put this X here, this diagram, the top diagram, is great for surface low pressure system, either intensification or development. Bottom here though, however, what's happening here? Look where my surface low is with the frontal boundaries. Look now where my 500 millibar shortwave trough is. That is not a good situation for that surface low. Because now you're getting sinking air motion, which is counteracting the upper level divergence. And it's actually becoming stronger. This downward vertical motion, that sinking air motion is becoming stronger. And this upper level 500 millibar trough no longer supports the surface low. So this surface low is going to begin to fill, which basically means that your surface low pressure is, you're going to start having barometric pressure rises instead of falling barometric pressure. All right, and this is a very bad situation. All right, so this right here would be your cyclolysis aspect. All right, this up here at the top is excellent. We'll just call it cyclogenesis up here. This is excellent for cyclogenesis. So I wanted you just to get a comparison of the differences between cyclogenesis and cyclolysis. Now for anticyclogenesis, this is the formation of a new high pressure or the intensification of an existing high pressure. Surface high is initiated by upper level features. Best places to find anticyclogenesis is ahead of the shortwave ridge, at or just ahead of the longwave ridge axis, and in areas of confluent or converging airflow aloft. Makes perfect sense. Look over here on the right. Our H represents our surface high pressure system. And it's a baroclinic system. It stacks back. It stacks back. It stacks back. Look at this. All the way up to 500 millibars. Now, what did we say was ahead of a shortwave ridge axis? You may have to go back and review my previous few training videos, but what's ahead of a shortwave ridge axis, a sawtooth line? This is going to be NVA. NVA here ahead of the shortwave ridge axis. NVA. Okay? This is going to be upper level convergence. So damper effect here. Okay? This is going to result in DVM, downward vertical motion. DVM, downward vertical motion. Okay? At every level ahead of the shortwave ridge axes, at every level here. From 850 millibars all the way to 500. And this surface high is being supported by this upper level shortwave ridge. All right, and if we look at the damper effect again, let's just draw it out. We want more mass coming into the column up here in the upper levels of the atmosphere than is being removed. So you notice my arrows here at the surface again are less. They're not as long as the arrows up here in the upper level of the air column. We have stronger incoming upper level convergence, or the addition of mass. If I put a plus sign there, I have more mass coming in at the top of the column than is leaving down here at the bottom of the column. And that's going to help support anticyclogenesis. All right. Additionally, we look at the long wave pattern At or just ahead of the long wave ridge axis is the favorable area. Let me go ahead and get this out. All right, so let's say this right here is my long wave ridge. And where is anticyclogenesis going to be favored? It's going to be favored right in here. Here's our ridge axis, our sawtooth line in the long wave ridge. Let's label this the LWR for long wave ridge. This is a favorable area right here. At and just ahead of the long wave ridge axis, this is a favorable area for anticyclogenesis. And also if you get confluent flow aloft. So now we're bringing these height contours closer together, right in here. That is indicative of confluence, directional convergence of air aloft, which is adding mass. It's adding mass. This confluent flow aloft is going to result in this damper effect down here that I drew out, where you're getting more air coming in at the top of the column than is leaving at the bottom of the air column. So for anticyclogenesis, its common factor for formation or strengthening of a high is convergence aloft. You have to add mass to your vertical air column. That's going to result in downward vertical motion, which is going to result in rising surface pressures, which is exactly what anticyclogenesis is about. The surface high is found in areas where there is significant upper level convergence. There's your addition of mass to that vertical air column, increases surface pressures. Surface anticyclonic circulation is going to increase with an increase in downward vertical motion. And the upper level convergence must remain stronger than the low level divergence for anticyclogenesis to continue. So anticyclogenesis is ahead of a short wave ridge where you have significant upper level convergence. The surface high is directly below the area of maximum convergence in the upper levels. And another significant factor for anticyclogenesis is diabatic cooling. So for high pressure systems at the surface to either develop or intensify, we want an underlying surface that is cooler. We want it, this is a great example of this occurs in the wintertime across Siberia, where you get a snowpack. The power of a snowpack cannot be overstated here, because if you have a snowpack, my ground is going to be much colder. The colder that surface is, the greater the potential for anticyclogenesis. We've seen some of the strongest baroclinic surface high pressure systems ever in Siberia, as an example, because of that snowpack. But if you don't have the snowpack, you don't have as cold of a surface for high pressure to really strengthen over, and you're going to have a different type of weather pattern. The air mass will not be as cold over a bare ground versus a snow-covered ground. So as air cools, it's going to sink, adding to the surface pressure and strengthening the surface high. All right, so the weakening, now let's go into anticyclolysis. This is the last topic we'll cover in today's training. Anticyclolysis is the weakening or dissipation of a surface high pressure system. The primary cause is loss of upper level support. Upper level convergence is either weakening or it's basically not occurring at all now. The short wave ridge moves directly over the surface high, pushing an area of upper level convergence ahead of it. But after that upper ridge axis passes, the upper level convergence is going to decrease in magnitude aloft, with upper level divergence occurring behind that short wave ridge axis. This decreases the downward vertical air motion and stops adding mass to the air column, causing the upper ridge to weaken. So this is a lot to digest. Let me draw this out and it'll make more sense. All right, anticyclolysis, simply put, don't need to draw this out. It's just the weakening or dissipation of a surface high. Primary cause is loss of upper level support. Well, let's see what happens here. This would be an example of loss of upper level support. Let's say, again, my arrows represent the magnitude or strength of upper level convergence, okay? So let's say my arrows are shorter. This is in the upper levels of the atmosphere. I still have downward vertical motion. Don't get me wrong, it's still there. But now let's say my divergence at the surface, my surface divergence is stronger at the ground. All right? So my low level divergence is stronger than my upper level convergence. This is weaker up here. I'm going to put a W. And at the surface, my divergence, so I have upper level convergence that's weaker. I have more air outgoing at the surface. So my overall downward vertical motion over time is going to decrease or become less intense. Now this can happen when you have, as an example, let me go ahead and erase this. Now, let's say we have that shortwave ridge axis, right? So this is our shortwave ridge axis, okay? Initially, things are great because guess what? Our surface high pressure system is being supported by this upper level ridge. If I were to draw a line, notice how it stacks back with height, see that? Now what's ahead of this shortwave ridge axis? Remember, we have an area of NVA, negative vorticity advection. We have an area of downward vertical motion, DVM, and we have an area of upper level convergence, ULC. So we're adding mass to the column ahead of the shortwave ridge axis. The surface high here is going to absolutely love this because we're causing stronger downward vertical motion. When you have more force per unit area at the surface, you're increasing your surface pressure. So more weight of the atmosphere is pressing down when we have this situation where you have the NVA ahead of the shortwave ridge axis, downward vertical motion, upper level convergence at the top of the air column. This is a great situation. This is the anticyclogenesis situation, okay? Now what happens though, what happens when we get, let's go over here, bottom right will be where we're going, okay? So now let's say my upper level ridge axis is over here. Here's my sawtooth line, all right? But now my surface high pressure is, let's see, right? My surface high pressure system is over here now. Uh-oh. This is the surface. All right, but uh-oh, right? Because now, what do we have? Let's see. On the back side of a shortwave ridge axis, after that ridge axis passes at 500 millibars, what's on this side of the ridge axis? We have PVA, positive vorticity advection. Not good for downward vertical motion. We have upward vertical motion with PVA here behind the ridge axis after it passes. And we also have upper level divergence. That is not good for this high pressure at the surface. It is not good. That's going to promote rising air motion. That is going to promote the upper level divergence is going to start removing mass out of the column. Not what we want for a surface high pressure system, specifically a baroclinic type. So that's what happens overall. We start adding mass to the column, cause the upper level ridge to weaken. The vertical motion is going to stop. It's going to be replaced by rising air motion. That's why it's so important to look at the positions of these short waves at 500 millibars in relation to where the surface high pressure and low pressure are located. All right, so the second way for the high pressure system to weaken at the surface is for it to move south. Why is that the case? Well, as the high pressure system, the baroclinic high moves south. Let me see if I can find my color code here. All right, so let's say this is the high pressure system initially, okay, over Canada, but it's going to continue to move towards the southeast. Over time, it's going to move into the United States. It's going to move into like the Dakotas and Minnesota, then the Midwest, then eventually down towards the mid-Atlantic and southeast coast of the US. But as it makes this move from the Canadian area down southeastward across the US, it's going to continuously move over warmer and warmer ground. By the way, this baroclinic high is also going to follow the strongest cold air advection areas, okay? Which is typically going to be out ahead of the baroclinic high because you have northerly winds. Bottom line though, going from where the surface high may have developed, it's extremely cold, you have diabatic cooling, you got a cooler surface beneath it. Maybe that surface is snow covered over Canada, but when it comes out over a bare ground as it moves southeastward towards the mid-Atlantic in the southeast, you're losing that source of cooling beneath this high pressure system, and it's going to cause the high to eventually weaken. And eventually, the center of this baroclinic high will actually be absorbed by the subtropical ridge over the Atlantic Ocean. It is also modified by the surroundings until it is no longer an identifiable center, and it just blends in with that semi-permanent pressure feature, the subtropical ridge. And then the final way to cause anticyclolysis is diurnal warming, believe it or not. During the daytime with the sun out, specifically when we get towards early spring, maybe late winter, early spring, even into the early fall season, the ground can still be fairly warm during the day with the sun out, and that is going to result in killing that baroclinic high. It's going to weaken, or that you'll notice the barometric pressure get lower and lower, that number. That's going to cause upper vertical motion. Whenever you have a warming surface, the air is going to want to rise and works against the influence of the upper level converging air. All right, so anticyclolysis, here's some examples again. This is the example of where, now this is the surface high down here. This is the surface high here at the upper portion. Let's look at these two diagrams, all right? All right, remember, NVA is out ahead of this thing. Upper level convergence is ahead of this shortwave ridge axis at 500 millibars. There's complete support to the surface high in this example. We're enhancing downward vertical motion. We're increasing surface pressures here, which is resulting in anticyclogenesis at the top. So this is anticyclogenesis up here. But at the bottom here shows your 500 millibar feature now is outracing your surface high. And that again is where we're on the back side of that shortwave ridge axis, where we now have, I probably should draw it in red again just to keep it simple here, right? So this is actually a red area here, where we have our PVA rather, PVA behind the shortwave ridge axis. You're going to get upper level divergence, and you're starting to get the upper vertical motion behind this shortwave ridge axis, which is going to result in this anticyclolysis of the surface high. Surface high is no longer supported by the upper level ridge at 500 millibars, and it'll begin to weaken. All right, so that will wrap things up. I'm going to do a quick summary here, and I hope you're having a wonderful Labor Day, by the way, everybody. So what we looked at today were four main processes when we talk about pressure intensity changes between lows and highs in the mid-latitudes. Cyclogenesis, forming or deepening of a low pressure at the surface due to increasing amplitude of the upper level trough. Cyclolysis, dissipation or filling of the surface low pressure system due to loss of upper level support as the 500 millibar shortwave trough overtakes the surface low pressure system. Anticyclogenesis is the formation or building of high pressure system, and this is due to increasing amplitude of the upper level ridge. And then you get anticyclolysis, the dissipation or weakening of a high at the surface due to loss of upper level support. In this case, for anticyclolysis, the shortwave ridge at 500 millibar overruns the surface high pressure system, that baroclinic high, and that results in PVA on the backside of that shortwave ridge axis, upward vertical motion. You start to see some of that loss of the mass of the air column, and that's going to result in lower surface pressures for the high pressure system. Now, all changes are directly influenced by the upper level features, by these short waves. And that's why I covered short waves in my last set of videos. I wanted to cover the short waves first so you'd understand those, and then we could talk more about how they impact these surface lows and surface high pressure intensity. Cyclogenesis and cyclolysis are directly linked to those shortwave troughs, the positioning of those troughs. Where's my PVA? Where's my NVA in association with these? Divergence aloft deepens surface lows, removes mass aloft at the top of the column. Upper level convergence, or convergence aloft, strengthens my surface highs. I'm adding more mass to the top of the column. And then we talk about the surfaces over which these high and low pressure systems move over. These highs and lows in the mid-latitudes are constantly on the move. The surface heating is called diabatic heating or diabatic warming. It helps to deepen surface lows due to rising air motion. It promotes rising vertical air motion. And that would be with a low pressure system here on the left, okay? When we talk about surface heating, low pressure systems are constantly seeking out these areas where it's a warmer surface. They're trying to survive, basically, these low pressure systems. So they're not going to go towards a colder area. They want to go towards a warmer area, which is helping to promote rising air motion in the vertical. Now, diabatic cooling strengthens surface highs due to subsidence or sinking air motion. And again, this diabatic cooling is so very important over here on the right with surface highs. a snow-covered ground, some of the strongest, greatest barometric pressures of high pressure in the winter. I believe it was over 31 inches at Agata, Siberia, on New Year's 1968, where there was just a thick, deep snowpack. You had very limited incoming solar radiation at that time of the year because it's the Northern Hemisphere winter, and it just really helps to strengthen highs. That's really why it's so important to get a snowpack down if you really want to see snow in the US in the wintertime. You want stronger cold air advection associated with these stronger high pressure systems coming out of Canada. Now I wanted to cover, that wraps all my slides up for this video, but I wanted to do one more quick summary. Yeah, I could use this slide. This is a great slide here. Okay, so let's talk about the relationship of shortwave ridges and shortwave troughs just one more final time. Okay, we're going to do this one more final time. So let's say this is a shortwave ridge at 500 millibars, and then we'll put this is a shortwave trough up here at the top, the U shape. And this is a shortwave ridge at the bottom, the upside down U shape, okay? Now, this is the shortwave ridge axis, represented by a solid dark line. This is your, so shortwave trough axis, solid dark line, shortwave ridge axis, sawtooth line, okay? Now, in all cases with shortwaves, this is the relationship of NVA and PVA. This is important to remember. All right, so we'll do PVA in red. I'll just put the letter P. Okay? And then with the ridge, shortwave ridge axis, PVA is going to be behind it or to the west of it. Okay? And then the NVA relationship in association with shortwave troughs and shortwave ridges, you're going to have NVA, so we'll represent NVA by the letter N, okay? And then you're going to have NVA right out ahead of shortwave ridge axis. So if you can remember this relationship, honestly, this is like so important. So with shortwave troughs here at the top, we have an area of positive vorticity advection, P, letter P in this case, a red circle. That's your PVA area. Vorticity values are rising. This is always going to promote, hang on here. This is going to promote upward vertical motion, UVM. It's going to promote upper level divergence at the top of the air column, ULD. Usually out ahead of the shortwave trough axis too, you'll get an area of warm air advection, WAA. Okay. The same thing is going to be down here behind the shortwave ridge axis. You're going to get upward vertical motion. Please forgive me for my letters. They really aren't that great. Upper level divergence. Okay. And you're going to get warm air advection here. Oh. Okay. And then that's associated with PVA, letter P. Well, PVA occurs out ahead of a shortwave trough axis. It occurs in the backside of a shortwave ridge. Now, let's do NVA, the characteristics of it, which are going to occur behind your shortwave trough axis. NVA is associated with what? What do we talk about? We have downward vertical motion, DVM, so sinking air, promotes high pressure and fair weather. Okay. We have upper level convergence associated with NVA. So the air is we're getting mass added to the top of the air column. We're accumulating mass, and it's also associated with cold air advection behind the shortwave trough axis. You have cold air advection, cold air moving in. And the same thing goes out ahead of this shortwave ridge axis. You have downward vertical motion, DVM. Okay. Gosh, that does not look like it's the right letter. You have upper level converging air at the upper level of the air column, adding mass, resulting in sinking air motion. And typically you get cold air advection out ahead of the shortwave ridge axis. Now keep in mind, the stronger the vorticity advection, the stronger the thermal advection, the deeper or more amplified these shortwave troughs and ridges are going to be. All right. So, but this is a very important concept in meteorology. You really need to examine. Okay, you really need to examine on the 500 millibar chart, the 700 millibar chart, and then your surface chart, which shows your surface highs and surface lows, your baroclinic highs and lows. You need to really know this down pat. Okay, this is really going to be helpful. The relationships. All right. So hopefully that helped kind of elaborate. I wanted to do this is like my summary here, okay? I have a chart, and if I can remember the next video, I'll show it at the beginning of the next video. It's kind of like a chart that you develop, and you look at the type of vorticity advection, the type of thermal or temperature advection, and you examine whether those two, vorticity advection and thermal advection, work for rising air or against rising air motion. And I'll show you that whole example and breakdown. I do have a picture of it from my meteorology school. I'll take a picture of it and I'll just throw it in the next video, because the next video is going to be very, very exciting. We're now in meteorological fall, and I want to really delve into the wave cyclone process. So surface low pressure systems, we're going to dive into the various stages of surface cyclones in the mid latitudes, the development, the intensification, the decaying stages of those. And some of this stuff we've learned in my previous training videos is going to tie in directly to it. And then my final training video is going to cover where in relation to surface lows that you find the heaviest precipitation. And we'll look at the synoptic situations as well that promote heavy snow and heavy rain. This is awesome stuff, guys. This is the dynamics. This is the why behind the what in meteorology. You know, as we live here at the ground, at the bottom of this ocean of air in the troposphere, you know, is it sunny today? Is it raining today? You know, how is the weather when we're, moving about on the ground here? It's all connected to these features in the upper levels of the atmosphere, these short waves. And those long waves as well kind of promote troughing and ridges and the type of weather we experience. It is just all connected, and it's awesome. Okay, that wraps up my training today. I hope you enjoyed it. And until next time, take care and God bless everyone.